This videocassette examines the life cycle and structure of tropical cyclones in conjunction with a case study of the 1983 Hurricane Alicia. The tape is organized into three main sections. First, an overview of tropical cyclone genesis, structure, and circulation. Next, a summary of methods used for tropical cyclone investigation. And finally, presentation of the Hurricane Alicia case study. Regions of tropical cyclone origin are quite distinct due to a number of conditions necessary for their development. In general, oceanic regions located at least several degrees of latitude away from the equator, with sea surface temperatures greater than 26.5 degrees Celsius, are areas of potential tropical cyclone genesis. Nearly one-third of all tropical cyclones originate in the western Pacific Ocean, with about twice as many in the northern hemisphere as in the southern hemisphere. Tropical cyclones do not form in the South Atlantic Ocean due to its cold sea surface temperatures. The vast majority of tropical cyclones develop within or just on the poleward side of the intertropical convergence zone. The remainder originate either as disturbances in the easterly trade winds or as baroclinic systems along stagnant frontal zones in the subtropics. Satellite imagery has shown that in the Atlantic Genesis Basin, a much larger percentage than the global average originate away from the intertropical convergence zone. During the period from 1967 to 1977, over one-quarter of all North Atlantic tropical cyclones developed from baroclinic disturbances and about half from trade wind disturbances. Climatological studies of tropical cyclone formation have shown that several conditions must be met before the initial disturbance can organize and intensify. These requirements are directly related to storm angular momentum and deep cumulus convection, and they can be summarized in the 6 physical parameters listed here. Observations indicate that tropical cyclones only form in areas where sea surface temperatures are 26.5 degrees Celsius or higher. This threshold is likely related to the fact that warmer ocean temperatures induce more sensible and latent heat transfer into the boundary layer, thereby reducing the convective stability. To support the deep cumulus convection associated with tropical cyclones, the atmosphere must be convectively unstable. In general, equivalent potential temperature gradients between the surface and 500 millibars must be greater than 15 degrees Kelvin for a tropical cyclone genesis to occur. Mid-tropospheric mean relative humidities of 50% or higher are necessary in order to prevent the convective towers in the developing storm from being eroded by entrainment of dry air. In addition, large relative humidity values above the boundary layer significantly increase the potential for latent heating within the system. Tropical cyclones only form in regions of positive lower tropospheric vorticity. Intense cumulus convection within the initial disturbance generates low-level horizontal mass convergence, which in accordance with the vorticity equation promotes an increase in the cyclonic rotation of a system if it's embedded within a field of positive vorticity. This establishes the feedback effect between latent heating, low-level mass convergence, and cyclonic spin-up known as conditional instability of the second kind, or CISC, often used to help explain the rapid growth of large-scale tropical disturbances. Because the effect of convergence in producing an increase in cyclonic rotation is reduced at extremely low latitudes, tropical cyclones do not form within about 5 degrees of the equator. Finally, vertical variations in the speed and direction of the wind are an important consideration. Large vertical wind shear prevents heat and moisture from increasing in the mid and upper troposphere, and the system becomes ventilated. However, if vertical shear is small, heat and moisture buildup can occur, thus promoting a gradual decrease in surface pressure. The life cycle of tropical cyclones can be categorized into 4 main stages, according to the amount of organization and the maximum sustained surface winds associated with the cyclonic circulation. Genesis of a tropical cyclone can only occur from a pre-existing unorganized disturbance. Although such disturbances are regularly observed in the easterly wind regime of the tropics, only about 10% of them organize and intensify to tropical storm strength. Development of a disturbance into a tropical depression can be attributed primarily to the CYCLONE positive feedback effect described earlier. Additional development requires a substantial decrease in mass and an increase in the angular momentum of the system. This is accomplished primarily through mass and momentum transports in the lower and upper troposphere, which are linked by the vertical mass transport within the system's deep cumulus convection. Together, these processes produce a spin-up of the cyclone vortex and a gradual strengthening to tropical storm intensity. Development to tropical storm strength is usually slow to occur, often taking several days. However, the transition to hurricane intensity can be very rapid, sometimes occurring in less than 12 hours. The primary features of a mature tropical cyclone and its radial mass circulation are illustrated in this cross-section. The center, or eye, of the storm is located at the far left. Several bands of intense convection, usually separated by rain-free areas, surround the eye. Heaviest rainfall and strongest low-level winds tend to be concentrated in the eye wall immediately surrounding the eye. Oftentimes, only the outermost rain bands are evident in satellite imagery due to the dense cirrus overcast nearer the storm center. The mass circulation within the storm environment is characterized by lower tropospheric inflow, which transports mass, angular momentum, and moisture toward the storm center. Upper-level outflow produces a divergence of mass and angular momentum. The vertical mass transport within the storm's convective bands is the primary mechanism for coupling of the lower and upper tropospheric flow patterns. In order to achieve the extremely low central pressure and intense cyclonic rotation of a mature tropical cyclone, the outflow in the upper troposphere must transport more mass away from the vortex center than the low-level flow transports inward. Likewise, the lower branch must transport more angular momentum toward the axis of rotation than the outward branch transports away. This imagery sequence of Hurricane Alicia provides an overall view of the large-scale horizontal motions associated with a mature tropical cyclone. Rather than being fixed relative to a point on the Earth's surface, individual images in the sequence are focused on the center of the hurricane, thus providing a storm-relative perspective. Intense cyclonic rotation about the vortex center is clearly evident. Several of the outer rain bands are visible, however those near the hurricane center are obscured by the cirrus overcast. Large-scale convergence is apparent in the low-level cloud motions, with divergence in the cirrus cloud field, especially to the east of the hurricane. Diurnal convective activity is present over eastern Mexico and most of the southern United States. The lack of cumulus development over southeastern Texas may be indicative of the subsiding branch of the mass circulation at the hurricane's outer edge. This sequence of Hurricane Diana portrays a very intense circulation with an extremely well-defined eye. The sloped structure of Diana's inner eye wall produces a bowl or stadium-like appearance. This so-called stadium effect is usually only observed in the most intense tropical cyclones. Because tropical cyclones spend most of their lifetimes over oceanic regions, obtaining sufficient data for their study has traditionally been difficult. Through the use of advanced satellite technology, it is now possible to examine the structure of individual storms while they are over the oceans. By combining these new techniques with more conventional methods, the modern meteorologist now has available 4 primary methods of tropical cyclone investigation. The most traditional of these is the compositing of data from several storms. This method has several drawbacks, including a tendency to smooth structural fields and the possibility of obtaining a meaningless average from 2 unlike quantities. The latter problem can often be alleviated by grouping the storms according to general characteristics such as size or intensity. A second widely used method is the simulation of tropical cyclones using numerical models. These models solve approximations of the primitive equations over a high-resolution 3-dimensional grid and are especially helpful in better understanding the role of individual physical parameters, such as sea surface temperature or vertical wind shear, in the development process. Despite numerous difficulties, a number of experimental as well as operational versions of these models have achieved considerable skill in forecasting the motion and intensification of actual tropical cyclones. A new perspective for tropical cyclone investigation emerged with the advent of global satellite imagery in the late 1960s. In addition to the capability for viewing all of the tropical cyclone origin regions simultaneously, geosynchronous satellites provide the means for nearly time-continuous monitoring of individual disturbances. Without question, the use of satellite imagery has improved meteorologists' understanding of tropical cyclones more than any other single factor. More recently, satellite-derived soundings have provided a vast amount of new information on the vertical and horizontal distributions of temperature, moisture, and wind in tropical weather systems. The following examples help to illustrate a few of the many applications of advanced satellite techniques in tropical cyclone research and forecasting. In the first sequence, visible imagery from August 17, 1983, is displayed at varying resolutions. A 24-kilometer resolution image is shown here. At this resolution, it is possible to view nearly the entire full Earth disk in a single image, allowing for simultaneous monitoring of tropical weather systems over a vast region of the Earth's surface. By sequencing or looping successive images at this resolution, cloud movements can be determined on a broad scale. This information can be used to infer large-scale wind patterns as well as temporal changes in the patterns. In this particular sequence, the intertropical convergence zone, the easterly trade winds, and the middle latitude westerlies are all clearly evident. The small, concentrated cloud mass in the northern Gulf of Mexico is Hurricane Alicia. As resolution is improved, the image field of view becomes smaller. Each doubling of resolution shown here produces a much clearer depiction of the cloud configuration associated with the hurricane. The highest resolution presently available from geosynchronous satellites is 1 kilometer. Sequencing of images at this resolution provides an extremely detailed view of the hurricane circulation. If the time interval between images were small enough, it would even be possible to monitor the development and movement of individual cloud elements within the hurricane circulation. Perhaps the most significant impact of satellite sounding technology has been over the vast ocean regions where very little data is available from other sources. These sequences of Hurricane Debby from September 1982 provide some examples depicting the use of satellite-derived soundings in tropical cyclone diagnosis. The first data set displays Visser atmospheric sounder, or VAS, data from 21Z on September 15th. The center of Hurricane Debby is located approximately 1,300 kilometers east-southeast of Cape Hatteras, North Carolina. Color enhancement of the infrared window channel image depicts a circular ring of intense convection, indicated by the white coloring near the center of the storm, associated with the hurricane eye wall. Cirrus clouds stretching to the northeast of the storm are associated with a trough in the westerlies. The mid-tropospheric water vapor channel indicates a region of high moisture content to the north, east, and south of the hurricane circulation. Drier air is present to the west of the hurricane. To the south, a narrow wedge of dry air appears to be entering the hurricane circulation. At this time, Debby was far from a major landmass. The 250 millibar geopotential height data from the closest radiosonde stations are shown in this image. Bermuda is located to the northeast of the storm center. The huge data void region in the western Atlantic is very evident. Next, geopotential heights from the 21Z VAZ sounding retrieval are added. Soundings can be generated in clear and partly cloudy regions. However, data gaps still exist in areas of dense cloud cover. The next sequence of images is from early the next morning. This data was obtained from the microwave sounding instrument aboard the NOAA 6 polar orbiting satellite. The oxygen absorption band near 60 gigahertz is not affected by water vapor or cloud droplets, allowing microwave radiation to pass through non-precipitating clouds. In this image, upper tropospheric temperatures, as determined from microwave channel soundings, are color enhanced. The dark blue and black regions indicate the upper-level warm core of Hurricane Debby. Recent advances in video computer technology have provided the capability for near-time continuous monitoring of tropical cyclones over extended time periods. This is demonstrated in the following sequence of infrared window channel imagery from Hurricane Elena. The sequence spans a 5-day period with a 1-hour interval between individual frames. The particular enhancement used depicts only mid and high-level cloudiness. At the beginning of the sequence, a well-developed upper tropospheric anticyclone is evident in the cirrus cloud motions over Cuba and the southeastern Gulf of Mexico. Under this favorable regime, Elena strengthened rapidly and became the first tropical cyclone on record to attain tropical storm intensity while still located over a landmass. Rapid intensification continued, and Elena reached hurricane strength while entering the Gulf of Mexico on the following day. During the next 48 hours, Elena's interaction with an extratropical trough over the southeastern United States resulted in several dramatic and difficult-to-forecast changes in movement just off the Florida coast. As the trough moved off to the east, Elena resumed a west by northwesterly heading, finally making landfall along the Mississippi coast. Sequencing the images more rapidly helps to illustrate the system's erratic movement as it interacted with the mid-latitude trough to the north. The next sequence displays color-enhanced water vapor channel imagery for the same 5-day period. Since this imagery is only available at 6-hour intervals, the sequence appears somewhat jumpy. Mid-tropospheric dry air behind the extratropical trough over the southeastern United States is very evident. Note how the dry air remains to the west of the hurricane and does not become entrained in the circulation. Further enhancement of the dry region occurs as it begins propagating westward at the end of the sequence. This may imply a decrease in convective stability ahead of the hurricane, which could have aided in its re-intensification as it resumed its westward heading. Analysis of a particular case study in conjunction with the capabilities of the Mercatus video computer is an excellent means of illustrating the tropical cyclone scenario. Hurricane Alicia, which formed during mid-August of 1983, was selected for this analysis because of its well-defined structural features, the availability of satellite data over the Gulf of Mexico, and the system's major impact on the United States. Alicia attained tropical storm intensity on August 15th while located about 200 kilometers south of the Mississippi Delta. During the following 24 hours, the system strengthened only slightly. By the afternoon of the 16th, the storm was heading northwest toward the Texas coastline. At this point, Alicia began to intensify more rapidly and reached hurricane strength just before 18Z on August 17th. Deepening continued until landfall, which occurred at approximately 6Z on the 18th. As Alicia crossed the coastline, central pressure was estimated at 962 millibars. Maximum surface winds were concentrated in the storm's eastern eye wall. Damage surveys by a team from the University of Chicago indicate that wind speeds in excess of 55 meters per second occurred over most of Galveston Island and along the western shore of Galveston Bay. Winds were significantly weaker to the west of the eye track. Such asymmetry in the wind pattern is commonly observed in mature hurricanes and is due to the effect of adding the storm propagation speed onto a symmetric storm relative wind field. Rainfall amounts were also greatest to the east of the storm track. Values in excess of 7 inches were common over most of Galveston and the Houston metropolitan area. The maxima to the northeast and northwest were associated with the passage of intense rain bands well away from the hurricane's central core. While these totals are by no means exceptional for a storm of Alicia's intensity, they did produce substantial urban flooding. The following sequences of infrared imagery span Alicia's entire life cycle from pre-development to decay. The time interval between images is 2 hours. On August 11th, a well-organized extratropical cyclone was located over Pennsylvania with a cold front extending southwestward to Oklahoma. Diurnal convective activity illustrates the location and southward progression of this front into the Gulf of Mexico. Alicia developed from the weak disturbance at the southwestern end of the decaying frontal boundary. All of the necessary conditions for tropical cyclone genesis were present at this time over the Gulf region, allowing for gradual strengthening of the system as it drifted southwestward. Convection associated with the developing cyclone displayed a pronounced diurnal tendency. Formation of a well-defined eye occurred as Alicia reached hurricane strength. After landfall, a rapid decrease in overall structure is apparent. Strong southerly flow in the mid and upper troposphere over the central United States then accelerated the weakening circulation northward into the Great Lakes region, where it merged with an extratropical frontal system similar to the one from which it originated. As the images are sequenced again, this time at a faster rate, note the strong upper-level divergence over the developing cyclone as indicated by the cirrus cloud motions. An expansive anticyclonic circulation over the southeastern United States is also clearly evident. This feature persisted throughout the period and was the primary steering mechanism for Alicia throughout its lifetime. Color enhancing the imagery helps to depict the areas of most intense convection, indicated by the red and white shading. Unenhanced regions imply low cloudiness or clear conditions. Again, notice the pronounced upper tropospheric divergence evident in the cirrus shield accompanying the tropical cyclone. The following segments of the videocassette will examine individual segments of Alicia's life cycle. August 14th through 17th comprised the Genesis stage. This sequence of imagery from August 14th depicts the system during its earliest development phase. Intense cumulus convection clustered south of the Mississippi Delta indicate the location of the frontal disturbance. Overshooting cumulonimbus tops near the center of the cluster are associated with the most intense convective cells. A well-defined cyclonic circulation in the lower troposphere is evident in the low-level cloud motions. Meanwhile, movements of high-level cirrus clouds indicate the presence of an anticyclonic circulation in the upper troposphere. The strong anticyclonic vertical shear implied by these cloud motions suggests that the disturbance had already dissolved its cold extratropical core and possessed warm core tropical characteristics. Further evidence of this is found in the weakening convection during the late morning and early afternoon hours. This represents the typical diurnal convective cycle of tropical weather systems and is caused by a reduction in convective instability during midday due to warming in the mid and upper troposphere through the absorption of shortwave radiation by clouds in these layers. The redevelopment of convective towers late in the sequence possibly indicates onset of the destabilization phase of the cycle, which peaks at night. Soundings from 12Z on August 14th for radiosonde stations along the northern Gulf Coast provide information on convective instability, middle-level relative humidity, and vertical wind shear in the cyclone genesis region. The first sounding from Apalachicola, Florida, displays moderate instability throughout the troposphere. The surface to 500 millibar gradient of equivalent potential temperature is well above the 15-degree Kelvin threshold for development. Moisture is abundant in the lower troposphere, but substantial drying is evident above 700 millibars. Vertical wind shear is weak with velocities at all levels less than 18 meters per second. Boothville, Louisiana, located at the southern end of the Mississippi Delta and much closer to the developing cyclone, displays similar overall stability, but with considerably more mid-level moisture. Convective towers rising through this air mass would have only a limited potential for entraining dry air. The vertical wind shear is again weak. Moving further west, the Lake Charles sounding resembles the one from Apalachicola, with comparatively dry conditions above the 700 millibar level. However, the overall stability at Lake Charles is greater due to warmer mid-tropospheric temperatures. This warming is possibly the result of large-scale subsidence to the rear of the frontal boundary which moved into the Gulf of Mexico. As in the other soundings examined, vertical wind shear is weak. The final sounding from Victoria, Texas, indicates significantly drier conditions throughout the troposphere. Although static stability and vertical wind shear are comparatively weak, this sounding is unfavorable for tropical cyclone formation due to the relative lack of deep moisture. By 12Z on August 16th, Alicia had strengthened to tropical storm intensity. Central pressure had lowered to about 1,000 millibars, and maximum sustained winds were near 45 knots. The 850 millibar streamline analysis for this period, based upon conventional data sources, indicates a well-developed anticyclonic circulation centered over the southeastern U.S., with easterly winds along the northern Gulf Coast. A broad region of southerly flow extends from Texas into the northern plains. The lack of radiosonde stations over the Gulf of Mexico and unavailability of Mexican reports makes analysis in the vicinity of the tropical cyclone impossible using only radiosonde data. At 200 millibars, a vast anticyclone covers the western three-quarters of the United States. Strongly difluent flow is indicated over the northern Gulf region, but again, the lack of sufficient data makes a detailed analysis difficult. In the sequences which follow, methods are demonstrated whereby data coverage over oceanic regions can be enhanced through the use of satellite-derived soundings. Here, 850 millibar geopotential heights from 12Z on August 16th are plotted for the radiosonde stations surrounding the Gulf of Mexico. Next, these values are compared to the 850 millibar heights, labeled in decameters, computed from the VAS sounding retrievals for the same time period. Close agreement is indicated between the two data sets. By incorporating these satellite-derived heights into gradient wind computations, coverage of wind data can also be greatly enhanced. The 850 millibar streamlines shown here are based only on VAS-derived gradient winds. The lack of a well-defined circulation in association with Alicia is the result of a substantial data void immediately surrounding the storm due to the inability of the VAS to obtain soundings in overcast regions. Wind information in these areas can be supplemented by using satellite cloud motion measurements. Here, the blue vectors indicate cumulus and stratocumulus cloud motions and represent the lower tropospheric wind flow. The yellow vectors refer to measured cirrus cloud motions, which depict the upper tropospheric wind flow. An improved representation of the overall wind field can then be obtained by compositing information from all data sources. These composite 850 millibar streamlines show a well-defined cyclonic circulation covering most of the Gulf of Mexico. Orientation of the streamlines suggests that the maritime tropical air mass over the southern Gulf of Mexico provided the major source of Alicia's low-level inflow, thus helping to ensure an adequate moisture supply for the system's increasing convection. Had the primary inflow been from the north or west, development may have been hampered due to an overabundance of dry air being drawn into the circulation. These 200 millibar streamlines were again produced by compositing data from conventional and satellite sources. They indicate strong upper tropospheric divergence in association with Alicia. As with the lower level inflow, the storm's upper outflow appears to be concentrated in its southern sector. Soundings from 12Z August 16th for the radiosonde stations in closest proximity to Tropical Storm Alicia are displayed in the following frames. For comparison, the nearest satellite-derived soundings are also included, as well as the satellite sounding for a point approximately 200 kilometers southeast of the storm center. Radiosonde data from Boothville was only available below 400 millibars. The temperature and moisture profiles indicate strong convective instability in the lower troposphere. This is supported by the values of 44 and -6 for the totals and lifted index respectively. Although some drying is evident between 900 and 600 millibars, the mean relative humidity in this layer is well above the 50% threshold. The VAS temperature profile is in close agreement with the radiosonde data. However, VAS dew points are noticeably higher, especially in the mid-troposphere. The discrepancy in wind velocities is due to the fact that the radiosonde values are in knots, while the VAS winds are plotted in meters per second. Similar comparisons can be made between the VAS and radiosonde soundings for Lake Charles. Here again, the temperature profiles show close agreement, but significant differences exist between the dew point curves. Winds at all levels are easterly with almost no change in velocity, resulting in negligible vertical shear. At Victoria, both soundings indicate substantially drier conditions at mid-levels. The wind profiles show easterly flow increasing with height, reaching speeds of 25 knots near the tropopause. Although stronger than in the previous soundings, the vertical shear is still not sufficient to inhibit convective development. The final sounding in this series is for a point approximately 200 kilometers southeast of the vortex center. A vase sounding was possible here because of its location in between rain bands. Note the much warmer surface temperature resulting from the strong sensible heating by the underlying warm ocean. The totals and lifted index values of 48 and -9 indicate extremely unstable conditions. The entire troposphere is nearly saturated, demonstrating the tremendous latent heating potential in this tropical air mass. In general, these soundings have shown that the northern Gulf region remained a favorable environment for continued development of the storm, allowing for Alicia's intensification to hurricane strength during the next 12 hours. At this point, Alicia entered the mature stage of the tropical cyclone life cycle. A particularly striking aspect of this stage in Alicia's life cycle was the rapid development of a cloud-free eye. Eye formation indicates the onset of strong subsidence within the vortex center, which acts to dramatically increase temperatures in the already warm core, producing a rapid decrease in central sea level pressure. The solid ring of convection surrounding the eye depicts the eye wall, where winds are strongest and rainfall heaviest. Further from the center, a banded structure in the convection is more evident. Rainfall intensities in the bands may often approach or even exceed those in the eye wall, and winds accompanying the strongest squalls may often exceed hurricane force. Note the narrow bands of cumulus clouds extending hundreds of kilometers into the Gulf of Mexico. These are associated with regions of enhanced low-level convergence, which tend to spiral toward the storm's center. They are referred to as feeder bands since they supply moisture and heat to the storm's convective core. Sequencing the images more quickly helps to show the vast low-level cyclonic flow surrounding the hurricane. Another interesting feature is the cycloidal wobbling of the eye as it moves on a northwesterly course. Although not well understood, eye wobble is frequently observed in mature tropical cyclones. The 250 millibar temperature field shown in the next image was derived from microwave channel soundings obtained from the TOVS instrument aboard the NOAA 6 polar orbiting satellite. The data clearly indicates the warm core upper tropospheric anticyclone associated with the hurricane, indicated by the darkest enhancement. Techniques have been developed for estimating tropical cyclone intensity using only microwave-derived temperature data. They allow for intensity determinations even for storms located far out to sea. In the case depicted here, a method developed at the University of Wisconsin gave an estimated central pressure of 965 millibars with maximum winds of 100 knots. These values compare closely to the 970 millibar, 95 knot values measured by reconnaissance aircraft. The three images in this sequence show 11 micron infrared window channel views of Alicia approximately 6 hours before landfall. As in the visible imagery shown previously, the well-defined eye is a very striking feature. Eye diameter has increased to about 50 kilometers by this time, which is unusually wide for a hurricane of Alicia's overall size and intensity. This was the last satellite imagery available prior to landfall. Observations from the S-band 10-centimeter radar at Texas A&M University, located in College Station, Texas, clearly depict the precipitation pattern associated with Alicia as landfall occurred. The precipitation-free eye and circular ring of intense convection associated with the eye wall are clearly evident. Several of the outer rain bands embedded within the overall circulation are also visible. Animation of these images shows rupturing of the eye wall as it moved inland and a noticeable decrease in the intensity of convection near the vortex center. Relatively strong convection persisted in the storm's eastern sector, while the western convection dramatically decayed. This was probably the result of dry continental air being drawn into the western portion of the circulation, while the eastern side continued to feed upon the vast supply of moisture over the Gulf of Mexico. Following landfall, Alicia continued moving on a northwesterly course. This track took the center very close to the Houston Area National Weather Service office located in Alice, Texas. The barometric trace from that station provides a classic example of the pressure changes accompanying a hurricane passage. The minimum pressure reading of 966.7 millibars occurred just before 6 a.m. local daylight time and was preceded by about a 6-hour period of rapidly falling pressure. A period of equally dramatic pressure rises follows the minimum. These changes are many times more rapid than would be experienced in an extratropical cyclone and help to illustrate the intensity of the horizontal pressure gradient in the eye wall. The slightly more rapid recovery is probably an indication of storm weakening as it moved inland. Visible imagery from the following day shows a much weaker circulation. The cloud-free eye has disappeared, and the banded convective structure away from the center had begun to dissolve. With the system continuing to move away from its source of heat and moisture, and with the enhanced boundary layer convergence due to increased friction, the central pressure rose rapidly and maximum winds decreased. By 0Z on August 19th, Alicia had been downgraded to a weak tropical storm with winds of less than 20 meters per second. The system had entered the decay stage of its life cycle. As with the majority of all tropical cyclones, Alicia gradually lost its warm core and mutated into an extratropical storm. During this transition, the system continued to produce substantial convective precipitation as it moved northward through the Great Plains. The rainfall, although very heavy, was generally beneficial to those areas since they had been experiencing a severe drought for much of the summer. Finally, in response to the influence of the mid-latitude westerlies, Alicia's remains accelerated northeastward and merged with an extratropical frontal boundary over the Great Lakes.